curved beam formula here. Okay. Okay. So the curved beam, as I was explaining earlier, that the curved beam formula is actually used when the curvature of the member is actually more pronounced. You can see that if you have straighter elements like this, okay, if we have straighter elements like this, then you might not be able to see the curvature which is being caused in these particular elements because of the application of loads. But when a certain kind of member is actually constructed in such a way that the curvature of that particular member is actually visible to the eye, it is much more visible to the eye, and is being constructed in this curve shape. So you are going to apply this curve beam formula. So always remember that if the radius of curvature is greater than 5, then the 5 times the depth of the member, so the flexural formula can normally be used to actually determine the stress. Okay. So by this we can say that for rectangular sections, for rectangular section, we can say that R divided by H is greater than 5. Okay. And so you can also say, for example, for this particular for this par- for this par- by this particular formula, you can say that if the stress that is being find used to find out by the flexural formula, okay, so it will be lesser than the stress calculated by the curved beam formula. Okay. And the error which is going to be caused here will be approximately equal to 7%. Okay. So this error is actually further reduced when the radius of curvature of the depth of ratio is more than 5. Okay. If the radius of curvature of the depth if the radius of curvature to the depth ratio is actually more than 5, okay, it is actually more than 5. So this particular error can be reduced here. So now, by the formula, the figure which you have studied there, if there is a particular there is particular value over there. I will have to draw the figure once again for your understanding, so that you can easily able to get that. That if you want to calculate now we want to calculate the strip original formula. Okay, the strip original length. Okay, so which strip we are talking about? We are talking about the area element D, which we have taken as dA. Okay, we are talking about that particular area element. So that was taken there in the formula. I'm going to draw that you remember that this particular strip was taken. A particular strip here was taken. This curved strip, and it actually had a distance from O. It was subtending the angle of d theta there, and the radius which was actually passing there was here. If you remember that figure, you almost have taken the screenshot for that, so you will have that idea. The radius for that is actually equal to r. So in order to calculate the strip length, this strip length, the formula for strip length is going to be equal to r multiplied by d into theta. Okay, this is the strip length formula. Please kindly wait. There's a noise disturbance. Let me close the door ताकि आप लोगों को फिर जरा आवाज सुनाई दे. ठीक है. Okay, so can you hear my voice loud and clear? आप लोगों को मेरी आवाज loud and clear आ रही है? Can you see me loud and clear? Okay. So now due to the rotation, the strip has to change the length. So for example, you can see that when the load is applied over here, and due to the rotation of this particular member, as you know that there is a certain kind of resistive moment is going to be applied to this member, so we will observe a certain change in the length. So now due to rotation, the strip total length, total change in length, okay, total change in length is going to be equal to r minus r into change in the theta. Okay, so now the strain in this particular figure is going to become equal to E, which is equal to change in length divided by original length. So here the change in length is equal to r minus r into change in theta divided by r d theta. Okay, so this is actually going to become here as this is going to become here as E equal to r minus r into change in theta divided by r d theta. So let us say that change in theta divided by d theta is actually equal to k. So what is k? K is actually constant for a particular element. This particular value of k is going to be constant for a particular element. Okay. So when we put these values, we will get E equal to k into r minus r divided by r. Okay, so unlike the case of the straight beam, the normal strain is a non-linear function of r. In fact, it varies in a hyperbolic fashion. Okay, so since the material behaves elastically, so we are going to apply the Hooke's law here. So by Hooke's law, we can say that stress is equal to E into E. So we can say that E multiplied by K into R minus R divided by R. Okay. Now to obtain the location of the neutral axis, as a resultant, internal forces caused by the stress distribution acting are the cross section to be equal to 0. Okay. Now let's say, for example, that the summation of forces as a resultant is going to be equal to summation of forces that are actually acting in the x direction. Okay. So we can say that integral applied is equal to change in the element dA, okay, which is equal to 0. So this equation is actually going to become, as the change is actually applied on the area, because due to application of the load, this dA is going to undergo certain changes. So this equation is actually going to become E into K into R minus R divided by R. Actually, I am putting this value, see this particular value, okay, this value over here. So this is going to become dA equal to 0. Okay. Now since we know that E into K and capital R are constants, they are actually constants. So we have R as A into dA divided by R minus A into dA equal to 0. Now we have to solve this equation for R. Okay. Now solving for R, we will get this. Let me draw a straight line. So we will get this as R equal to A divided by dA by R. So let me write down for your ease so that you remember all these values what you have studied there. By comparing from the figure, you will remember that R is equal to the location of the neutral axis. It is the location of neutral axis specified from the center of curvature O of the member. Okay. Next is capital A. So it is actually the cross-sectional area of the member. The cross-sectional area of the member. What about now? Small r is actually equal to the arbitrary position of the area element dA, the arbitrary position of area element dA on the cross section specified from the center, specified from the center of curvature O of the member. अभी जो आप लोगों ने इस पिक्चर्स के स्क्रीनशॉट्स लिए हैं ना, तो उसको देखते हुए ये वैल्यूज उसके साथ कंपेयर करें कि जो मैं यहाँ पे लिख रहा हूँ, जो मैं यहाँ पे बोल रहा हूँ, क्या वो उसके बराबर है कि नहीं है. ठीक है. नाउ df is actually equal to stress into dA, and dm is actually equal to dfy, which is equal to stress into dA into y. So now m is equal to y into stress into dA. Okay. As we know that since y is equal to r minus r, so we will get m is equal to a into r minus r, e into k into r minus r divided by r into dA. So now, expanding and realizing that E, K, and R are constants. So this equation is going to give this equation is going to give us M equal to E into K into R square, applying the integral A dA divided by R minus 2 R into integral dA plus integral A R into dA. So now R is equal to A by dA. So we will get this equation as R bar equal to sigma R into dA by A, and here we are going to get this as sigma integral R into dA equal to R bar into A. Okay, so this equation is furthermore going to become M is equal to E into K into RA minus 2RA plus R bar into A. Okay, and furthermore is going to become M is equal to E into K into A into R bar minus R. So E into K is equal to M divided by A into R bar minus R. So as we know that stress is equal to E into K into R minus R divided by R. So which is actually equal to M divided by A into R minus R R bar minus R, okay, multiplied by R minus R divided by R. So the formula for stress is going to become equal to M into R minus R, okay, divided by A into R into R bar minus R. So this is the formula for calculating stress in a curved beam. Okay, this is the flexural formula for calculating the flexural stress in the curved beam. Okay. So आप लोग को मेरी आवाज आ रही है? Can you hear me out?
Yes, sir.
मेरी आवाज आ रही है आप लोगों
Yes,
को?
sir. आ रही है सर.
So so as you can see that this is the general formula in order to calculate the flexural stresses that are being caused due to the loads applied in a curved beam. Okay, it is actually known as the curved beam formula. Okay, it is actually known as the curved beam formula and is used to determine the normal stresses distribution in a curved beam. Furthermore, this formula can be simplified as as we know that y is equal to r minus r, okay, which is equal to r is equal to r minus y. So E is equal to r bar minus r. In case of eccentricity, if you have certain kind of eccentricity here, so stress is equal to m into r minus r divided by a into r bar minus r. So this formula is become equal to m into y, okay, divided by a into e into r minus y. Okay, this is another general form of the formula for the stress that can be calculated for a particular kind of curved beam. Okay, now let us start solving the problem here. Okay, let us calculate a problem. So I'm going to write down the equation here. Sorry, I'm going to write down the statement here. A steel bar having a rectangular cross section, a steel bar having a rectangular cross section is shaped into a circular arc as shown. This is the circular, and this is the steel bar, which is actually being shaped into a circular arc. Okay, so this circular arc has a cross section, and I'm going to draw here the cross section here as it has a cross section of 2 inch, and here it is also equal to 2 inches. Here it has an element of a small element, that is element is actually equal to dr, and this particular area that is selected is actually equal to dA. So here in this case you can see here that this radius is actually equal to r1, and it is actually equal to 9 inches. Okay, and this is actually equal to r r0, and it is actually equal to 11 inches. Now, what is further asked in the question? The question says that if the allowable normal stress is 20 ksi, okay. Now, if the allowable normal stress is 20 ksi, so determine the maximum bending moment M. You have to determine the maximum bending moment M that can be applied to the bar and also we are asking that what will this moment be if the bar was straight. So let me repeat the statement of this particular question, that a steel bar having a rectangular cross section is shaped into a circular arc as shown. If the allowable normal stress is 20 ksi, so determine the maximum bending moment M that can be applied to the bar what will this moment be if the bar was straight? Okay. So they are actually asking the moment value in this bar in both conditions in its original form, that if this bar is straight, what is going to be the moment, and if this bar is in curvature shape, so what will be the value of the moment for here. Now let us start solving this question here. Solution. Now since the moment tends to increase the bar's radius of curvature, it is positive. Okay, this moment is actually tending to increase the radius of curvature. So this moment is going to be taken here as positive. Okay, it is actually increasing the radius of curvature here. So it is actually going to be taken as positive. So to locate the neutral axis, we have we have r equal to a divided by integral of a into dA divided by r. So here we know that the area of this bar is equal to 2 multiplied by 2 inches, which is equal to 4 inch square. Now integral a into dA by r is equal to 11 inch and 9 inch. Okay, and we put this value, we will get as 2 into dr divided by r. So this value is going to become equal to 2 into natural log of r, which is equal to 11 and 9. So we will get this value of 0.40134 inches. Okay, नेचुरल लॉग एल एन की वैल्यू जो है, ठीक है, वो कैलकुलेटर में आप लोग को गिवन होगी, तो कैलकुलेटर में जब आप लोग वैल्यूज पुट करेंगे तो आप लोग को इजीली इसकी वैल्यू जो आप लोग के पास निकल आएंगी. ठीक है, सो पुटिंग दिस वैल्यू, इस वैल्यू को हम लोग कहाँ पुट करेंगे, इस वैल्यू को हम लोग इस इक्वेशन के अंदर पुट कर देंगे तो हमारे पास वैल्यू निकल आएगी r इक्वल टू 4 डिवाइडेड बाय 0.40134, which is equal to 9.9666 inch raised to the power 4. So it is now stating that the normal stress reaches its maximum at the top or at the bottom of the bar. And so we must compute the moment m for each case separately. Okay, since the normal stress at the top is compressive, because as we know that the normal stress at the top is actually compressive. Okay, so sigma is actually going to become equal to m into r minus r, or this is this is r minus r naught divided by a into r naught into r bar minus r. So you will get this value as minus 20 equal to m. I am putting this minus as the stress that is actually applied. I am considering it as the stress is actually compressive. Okay, so I am putting this minus value over here. So m into 9.9666, okay, minus 11 divided by 4 into 11 into minus 9.966. Okay, so we will get this value as m is equal to 28.39 inch kip. This is going to be the value for moment. So now at the bottom of the bar, normal stress is tensile. Okay. Now at this bottom of the bar here, the normal stress is actually going to be tensile. Okay. This stress at the bottom of this bar is actually tensile. So
Sir,
we will get the value of stress
sir,
equal to
excuse me.
plus 20 ksi. Actually, we are taking compressive stress here as negative. So when at the bottom of the bar, here we are actually this value of moment has been calculated at the uh, at the top of the compression, at the top of this particular bar. At the top, sigma at the top is actually equal to is actually compressive. Okay, it is actually compressive and it is taken as positive, and sigma at the bottom is actually tensile. Okay, and it is taken as negative. No, sorry, no, at the top it is taken as negative. Okay, and at the bottom it is taken as tensile, so it is taken as positive. Okay, now sigma here in this case is going to be equal to m into r minus r I divided by a into r I into r bar minus r. So we will get this as this r bar here is actually equal to 10. Okay, इसकी वैल्यू आप लोगों के पास 10 होगी. ठीक है. So we will write down this equation as sigma equal to m into r minus ri divided by a into ri into r bar minus r. So putting these values, we will get 20 equal to m into 9.966 minus 9 divided by 4 into 9 into 10 minus 9.966. So m is going to be equal to 24.83 inch kip at bottom of this bar. Okay, now as you can see that the maximum moment that can be applied is 24.83 inch kip, and so the maximum normal stress occurs at the bottom of the bar. Okay, now the compressive stress at the top of the bar is then equal to compressive stress at the top of the bar is going to become equal to sigma into m into r minus r naught divided by a into r naught into r bar minus r. So we will get this value as 24.83 into 9.966 minus 11 divided by 4 into 11 multiplied by 10 minus 9.966. So we will get the value of stress equal to minus 17.49 KSI. So now as we have said that this particular shape is actually of that of the hyperbola for this curvature of the beam. So when we are going to draw this particular stress distribution here, so it will appear like this. Okay, आप लोगों के पास कुछ इस तरीके से appear होगी. It will be like this. Okay, so here at the top the stress is going to be equal to 17 point, sorry, 17 is equal to 17.49 KSI, and here it is going to be equal to 20 ASI. So that is how going to be the stress distribution over here. Okay. Now let us solve another problem on this particular topic. एक और प्रॉब्लम हम इसके ऊपर सॉल्व करते हैं, ठीक है? आप लोग को मेरी आवाज आ रही है? कैन यू हियर मी आउट? मेरी
Sir.
आवाज लाउड एंड क्लियर है जी?
Yes, sir.
अच्छा,
जी सर।
कहीं पर कोई मसला हो तो फिर मुझे बता दीजिएगा, ठीक है? अच्छा, नाउ इफ यू रिमेम्बर, हमारे पास हमने एक जो है एक हमारे पास जो, ठीक है, पार्ट इसका रह गया, ठीक है, कि इसमें दूसरे पार्ट में हमसे कहा गया था कि दूसरे पार्ट में इसमें हमसे कहा गया था कि फॉर एग्जांपल अगर आप लोग के पास ये मेंबर स्ट्रेट हो तब आप लोगों के पास क्या होगा, ठीक है? अभी तो आप लोगों ने इसके कर्वेचर का जो है आप लोगों ने पूरी कैलकुलेशन की है ना, कि कर्वेचर में आप लोग के पास क्या सीन, यहाँ पर आप लोग के पास स्ट्रेस डिस्ट्रीब्यूशन आप लोग के पास क्या आएगी। अगर इस मेंबर को आप लोग स्ट्रेट लेंगे तो आप लोग को क्या होगा। मैं लेट मी टेक यू टू द अपर स्लाइड ताकि आप लोग को याद आ जाए, ठीक है? यू कैन सी दैट what will be the moment if the bar was to be straight। अगर बार आप लोग के पास स्ट्रेट होगी तब आप लोग के पास मूवमेंट क्या आएगी। हम लोग क्यों कर रहे हैं, ताकि हम लोग एरर कैलकुलेट कर सकें कि दोनों के दरमियान हमारे पास एरर जो है वो कितना आ रहा है, ठीक है? सो फॉर एग्जांपल if you say that if the bar was straight, if the bar was straight, so sigma is equal to mc divided by I. So it is equal to 20, which is equal to m into 1 divided by 1 by 12, 2 into 2 cube. So you will get m is equal to 26.67 inch cube. Okay. Now by curved beam formula, okay, by curved beam formula, we calculated that the maximum stress, the maximum moment that is occurring here is equal to 24.83 inch kip. So the percentage error is here is actually going to be equal to the error is actually going to be equal to 26.67 minus 24.83 divided by 26.67. So the error here is actually equal to 7.4%. So it is approximately equal to 7% here. Okay. So you can see that the error that is actually being accumulated here in the calculation of the स्ट्रेट मेंबर एंड द कर्व मेंबर इज एक्चुअली इक्वल टू 7%। यानी इसका मतलब आप लोग के पास क्या है, ठीक है? इसका मतलब ये है कि आप लोगों के पास जो कर्व बीम फार्मूले से आप लोग के पास जो वैल्यू होगी, ठीक है, उसमें आप लोग एज कम्पेयर टू स्ट्रेट मेंबर आप लोगों ने क्या करना है, उसमें 7% आप लोगों ने जो, ठीक है, उसमें कमी करनी है। जब 7% आप लोग उसको रिड्यूस कर देंगे तो तब जाकर आप लोगों के पास जो मोमेंट की वैल्यू आएगी दैट विल बी फॉर द स्ट्रेटर मेंबर जो मेंबर स्ट्रेट होगा उसमें आप लोग के पास आएगी। तो दोनों कैलकुलेशन में आप लोग के पास जो डिस्टेंस आप लोग जो फर्क आप लोग के पास आ रहा है दैट इज एक्चुअली इक्वल टू 7% एरर, ठीक है? सो
सर कुछ में सर
आई होप यू विल बी आप लोग को इस प्रॉब्लम की समझ आ गई होगी। आप लोगों को इस प्रॉब्लम की समझ आ गई है?
एक्सक्यूज मी सर।
जी, आप लोग को प्रॉब्लम की समझ तो आ गई होगी ना?
सर
Now this is the center of the curve, and from this center of the curve, this distance is actually equal to 200 millimeter. Distance to the center of the curve is actually equal to 250 millimeter, and distance to the outer portion of the curve is actually equal to 280 millimeter. Now this distance here, it has been mentioned here that it is like this shape, ठीक है, इसके आप लोग के पास जो shape है आप लोग के पास इस तरीके से आ रही है, ठीक है, like this. So it is actually equal to 50 mm. It is also equal to 50 mm, and it is equal to 30 mm. Now okay, what is the problem stating now? The problem statement is that the curved beam has a cross sectional area as shown. So if it is subjected to a bending moment of 4 kilonewton meter, determine the maximum normal stress developed in bar. So this curve beam is has a cross section. The cross section has been shown here in the figure. Okay, the radius and the cross section values and the moments that are being applied over here is shown. So it is subjected to a bending moment of 4 kilonewton meter. So we have to determine the normal stress that is being developed in the bar. Now, since the moment tends to decrease the bar's radius of curvature, okay, this moment is actually what is this moment doing? This moment is actually trying to decrease the radius of curvature of the bar. Okay, this radius of curvature of the bar is actually decreasing. Okay, so here the moment is actually going to be taken as negative. This moment is actually going to be taken as negative. Okay, now summation of area is equal to 0.05 into 0.05. We are talking about this dimension. Okay, plus half of 0.05 0.05 and multiplied by 0.03 for this dimension. So we will get summation of area equal to 0.00325 meter square. Now we are going to determine the location of the centroid here. Okay, so the location of the centroid is determined with the reference to the center of curvature. Okay, it is going to be determined with the reference of center of curvature. So this is the formula for determining the location of center of curvature. So we are going to put values here as 0.05 multiplied by 0.05 into 0.225 plus this is 0.325 actually and plus half into 0.05 into 0.03 into 0.26. Let me correct this. This is 0.25. Okay, this is 0.26. So divided by 0.00325. So our bar is actually become equal to 0.23308 meter. Now let us solve further this problem now. So summation A is equal to dA by R, and so we have to calculate this value. So for calculating this value, it is going to become equal to 0.05 into natural log of 0.25 divided by 0.20. We will get this value as 0.011157 meters. So for rectangular portion and for triangle, summation A into dA by R is equal to B into R2 divided by R2 minus R1 into natural log of R2 by R1 minus B, which is equal to 0.05 into 0.28 divided by 0.28 minus 0.25 into natural log of 0.28 divided by 0.25 minus 0.05. So it is going to become equal to 0.0028867 meter. Now we are going to find out the location of the neutral axis. So location of neutral axis is equal to R, which is equal to sigma by A divided by sigma of integral A into dA by R. So it is equal to 0.00325 divided by 0.011157 plus 0.028867. Both these values are added here. Okay, दोनों वैल्यूज को हम यहाँ पे ऐड कर रहे हैं. ठीक है, तो हमारे पास इसकी वैल्यू क्या आ जाएगी? इसकी वैल्यू हमारे पास आ जाएगी is equal to 0.23142 meter, which is the value of R. So the maximum normal stress the maximum normal stress is either going to be at point A or point B. Where is point A and point B? This is point A. Okay, this point is taken as point A, or this point is taken as point B. Okay, so the value is going to become as normal stress at B is equal to sigma into A, which is equal to M into R minus R naught. A into RB is actually RB. Okay, A into RB, R bar minus R. So putting the values, you will get sigma A equal to minus 4 into 0.23142 minus 0.28 divided by 0.0032 into 0.28 into 0.23308 minus 0.23142. So we will get value of sigma A equal to 129 megapascal. Similarly, sorry, this is sigma B. This is going to be sigma B. Okay, this is sigma B. And for sigma A, when we put the values, formula for sigma A will be equal to M into R minus R A divided by A into R A into R bar minus R. So sigma A is going to become equal to, when you put the values, is going to become equal to minus 116 megapascal. So you can see here that the maximum stress that is actually occurring here, the maximum stress that is actually occurring here is at point B, and it is actually equal to 129 megapascal. Let us draw this diagram over here like this. This is point A, this is point B. Okay. So it will be a hyperbolic shape. Okay, this is 116 megapascal, and this is going to be 129 megapascal. So that is the end of today's lecture. I hope you would have understood the topic well, and let me now stop the presentation. If you have any questions, you can ask now.